No way! Yeah, Dmitry Pavlovich, please wake up now. We are filming this very important scene. I'm waking up. What again? Hello? My name is Dmitry. Welcome to the DPLABS channel. Today we're going to tell you about heat engines based on the organic Rankine cycle. We're going to start building our test stand for all of this. It's going to be very interesting. Ladies and gentlemen, in the previous video I told you how you can use low potential machines. Potential thermal energy, for example from water in a deep well, air or geothermal heat sources for efficiently heating your home in this informative series about heat pumps. That's all well and good, but many people would like to utilize low potential energy directly to generate electricity. For this specific purpose, we can effectively use a heat engine based on the organic Rankine cycle. What is that? As you know, there are heat engines that operate on steam energy. For example, consider steam turbines, piston-driven steam engines, and various other similar mechanical devices. The overall efficiency of such powerful machines, for example large steam turbines and modern power plants, now consistently reaches approximately 40 to 45%. But the temperatures of the working fluid, water, in modern turbines range from 300 to 500 degrees with enormous pressures. In our particular case, we unfortunately do not have heat sources with such exceptionally high temperatures. All we can realistically make do with for achieving reasonable efficiency is, for example, the exhaust temperature of internal combustion engines or the heat generated from cooling certain technological processes, such as extrusion processes and so on, or alternatively, we can utilize geothermal heat sources. For example, if we take a source with a temperature of 350 Kelvin and a delta, or difference between heating and condensation of 80 Kelvin, then the thermal efficiency of such a machine will be 20%, which is actually not bad at all, considering that this energy is not really needed by us. We either have to dispose of it, or we can extract it from the ground. But in reality, the mechanical efficiency, I think at such temperatures, is only about 10 to 12%. What exactly can we effectively use as the actual heat engine? We can use a piston engine, and we can also use various types of turbines. Both axial and centrifugal types are commonly used. We can also utilize a scroll compressor. For example, a scroll compressor is a reversible machine, which means it can operate in both directions. We can also use a screw compressor. The specific operational characteristics of the organic Rankine cycle are defined by the fact that we utilize organic substances as the working fluid. Most frequently, various types of freons are employed for this purpose, because they are convenient to work with, allowing for the selection of the required boiling point, and oil dissolves within them. They are non-toxic, and a number of these are also non-flammable. Now I'll explain how we will select the working fluid. That is, the working fluid, we will be using various freons, must meet the following parameters. The main one is the pressure at our operating temperature, which is the temperature of our heat source. It should absolutely not exceed the mechanical strength, nor the operating pressure of our heat engine system. In this case, we will initially use scroll compressors for testing. In our case, that's about 25 to 27 bar. And also, its condensation temperature should be kept as low as possible within reasonable and practical limits so that we can achieve the largest possible delta. Right now, I think at heater temperatures up to 150 degrees, and the condenser temperature is about 10 to 12 degrees Celsius, and these are the precise temperatures we will utilize and thoroughly test, for example, with Freon R11. This particular Freon was originally employed as a crucial foaming agent, as well as for its essential use in low-pressure refrigeration systems, specifically those equipped with specialized compressors. Its boiling point, which is the temperature at which a liquid turns into a gas, is 23 degrees. And the critical point is specifically defined as the precise conditions of pressure and temperature at which the liquid... At this point, we can no longer distinguish the boundary between vapor and liquid. The liquid transitions into a supercritical state. This is neither vapor nor liquid, but a specific state. And we can't work with this state because it's quite unclear how to effectively work with it. In short, compressors are simply not designed to operate efficiently with supercritical fluids. The critical temperature of R11 is approximately 300 degrees Celsius, so it should suit our specific needs just perfectly fine. Its price is around 2,500 per kilogram. We've bought some and we'll give it a try. It's non-flammable and oil dissolves in it. Currently R11 Ephrion is. In similar setups, it is used as a replacement for R245. It costs about 4,500 per kilogram. It's very hard to find, especially in small quantities. We can also try using flushing refrigerant R141B as a test. Its boiling point is 49 degrees, but the other parameters aren't really important. It can even be stored in canisters because of its high boiling point. This immediately raises the question, why can't we use standard refrigerants with a low boiling point like R22? R22 is actually a pretty good refrigerant, but at our working heater temperature of 150 degrees, R22 would have long since gone into a supercritical state. Plus, the pressure of this gas at 150 degrees, I think, would be around 100 bar. That would exceed the operating parameters of our compressor. We also can't use propane. First of all, it's quite dangerous because it's highly flammable, and secondly, its operational parameters would be even worse. We also certainly can't use something with a very high boiling point like, I don't know, ethyl alcohol, for example, because its condensation temperature is high, and so, for example, the vapor pressure at 150 degrees would be at best 3 to 4 bar, which is considerably too low for our specific requirements. Therefore, we absolutely need to carefully select a suitable substance such that at the elevated temperature of the heater, the resulting pressure precisely approaches the absolute maximum operating pressure of our sophisticated heat engine system. Then everything will work as it should. To thoroughly test all of this, we will carefully assemble a dedicated test stand. This stand will prominently feature an electric heater with a significantly extended heating surface. We specifically, as you'll see, put the heating elements inside metal tubes to prevent local overheating of the freon, because at high temperatures freon can decompose, releasing harmful substances and generally break down. We really need to heat it quite very evenly. After this heater, we will then proceed to our compressor, which is designed to function as a heat engine. Subsequent to this, the freon will condense, entering the condensation pump, and the pump will send it back into our heater. We will generate electricity from the compressor, which we will use to power the heating elements. In this way, we will observe how much energy we spent and how much we produced. Well then, gentlemen, let's move on to our test stand, and I'll explain in detail how we're going to assemble it. So gentlemen, let me start telling you a little bit about our stand. The stand isn't new. It was already partially assembled before, but we actually had to redo it. First of all, I didn't have such great guys as Nikolai and Vanya. As you can see, it's quite hard for me to do everything with just one hand, and the others don't really understand precisely what to do. So in short, we decided to redo it. One of the main reasons was a problem with this specific heater. It had an original standard heating element, and the working fluid would consistently overheat on the surface of the element. That is, the overall surface area of the heating element was quite considerably small. So what exactly did we decide to do to address this issue? Let's start with the heater, which you've already seen in an interesting video. Someone correctly said, yes, it's an electric boiler. So what did we do? We took a thick-walled pipe. We completely welded it shut and then welded in 1-inch thick pipes. We inserted two powerful 2-kilowatt heating elements into these 1-inch pipes. These are indeed 2-kilowatt heating elements, and filled everything with aluminum for much better heat transfer. As a direct and significant result, the surface area is quite large, and the heat load is not that high, meaning our working fluid will heat up evenly across the entire surface. We'll install a controller to precisely regulate the power as needed. So what happens next? Next, there's a crucial moisture separator here, so the superheated steam comes in from here. There's a little coil inside, and any droplets of unvaporized liquid flow back into the heater, while the properly vaporized liquid, the steam, exits here. We won't use this sight glass because it's inherently risky. It simply cannot handle the extreme temperature. So we'll remake it. We'll use this thing as a viewing window to clearly see what's going on inside. Then the steam will go to our heat engine. Those who watched the games on the channel a year ago might recognize it. It's been modified into a DC generator. It got a bit jammed, but we'll sort it out and thoroughly test it. You can also see a DC compressor from Tesla here. It's basically a Tesla air conditioner compressor, and it can easily generate electricity. I just had to take it apart and carefully remove the check valve. Even if you just blow into it with 5 to 7 bar of compressed air, it works quite effectively. We won't bother with oil, it'll just vigorously spit it out. It spins quite actively and utilizes energy very well. Vanya and I tried spinning it with nitrogen at 20 bar, and it seemed to work quite effectively. And it was cooling. The air at the inlet was at room temperature. And at the outlet, it cooled down to minus 35 degrees. And this little compressor was generating 6 kilowatts of electricity. So I think it will fit very well here. It's designed for R134. But I think it can handle 20 to 25 bar, it won't explode. After that, everything will go to the condenser. The condenser here is small, so we plan to put in a donut-shaped one like this. That should do just fine. Here is the water circuit, supply and return. After that, it will go to the condensation pump. Here it is. The condensation pump was also made by Igor Negoda. We're going to modify it a bit now, because it jammed after my experiments as well. The oil got coked up in there. This is a motor from a rotary compressor. A gear pump is attached to it from directly below. Here it is, indeed clearly installed right here. And everything is welded shut, completely sealed. It pumps everything quite energetically. The good thing about a gear pump is that even if the vapor phase gets through, it quickly spits it out because of the airiness. It can generate a decent amount of pressure. In other words, it can easily push out 20 bar, no problem. There will also be filters installed here. We'll use refrigeration filters since they're suitable for the pressure. Also pressure gauges and so on. We'll set up a control system here. Everything will be nice and tidy here. And then we'll start testing. I think you'll see it soon. Right now we need to weld everything and get it in order. And then we're good to go. Before charging, the system will be vacuumed. And then, without any air present, we'll fill it with refrigerant. So what do we have here? What refrigerants do we have? Here we have 141B, flushing refrigerant, expanded from the heat. Its boiling point is 49 degrees. We also have, with a boiling point of 42 degrees, the so-called dry water. It's heavy. Maybe we'll try it too. And let me show you. We've stocked up here. This is our favorite. I think it will work best for our specific requirements for our current project. This is our truly impressive and powerful R11 cylinder, this particular unit. I think we'll start with it very soon indeed, I believe, with great anticipation. So what's next on the agenda? We will thoroughly test this on a relatively small scale. If everything works out perfectly fine for us, well, it most likely will indeed work fine. If it doesn't completely explode, which it absolutely should not in principle at all. The pressure isn't that high, and if anything, we'll just install some kind of safety valve, just in case. And we'll try it out. I have a large screw compressor, so we'll use that, and then we'll make everything more robust, including the heater and so on. And then we'll test it on a larger scale. In the future, I'd just like to make something like, for dedicated fans of alternative energy, let's call it, quite simply, a runs-on-nothing engine. I am referring to an engine based on the organic Rankine cycle, which will effectively utilize the Earth's natural heat as its primary heater and the surrounding atmosphere as its essential cooler. In the warmer summer months, the Earth itself will serve as the primary cooler and the atmosphere will function as the heater, and conversely, in the colder winter period, it will be precisely the other way around. With a significant temperature difference of 20 degrees, specifically 20 kelvins, which we can certainly achieve, well, the overall efficiency will be about 1.5 to 2%, but at least it will indeed run, and the energy itself is completely free, just like everyone truly loves. If we were to make a truly huge engine of infinite size, then we would certainly get infinite energy. So the main thing is that at least our efficiency is enough to overcome friction and other such things. But with larger sizes, that's not hard to achieve. But I think a bit later we'll make something like that as an experiment. Gentlemen, that's all clear. Experiments and so on. But in what areas of our lives can we actually use this? Well, the very first thing that immediately comes to mind is utilizing the energy from, for example, the exhaust gases and waste heat of an internal combustion engine. For example, we take some diesel engine where 60 to 70% of the energy is lost as heat. The exhaust temperature is quite high. The temperature of the coolant is not very high, about 100 degrees. We can effectively make a two-stage Rankine turbine, first using the high temperature of the coolant and then subsequently the elevated temperature of the exhaust. And I think in principle we could squeeze out even more with all the nuances. We could get an efficiency of about 20 to 25%, and then the efficiency of our diesel engine would not be 40% but 65%. For a large stationary generator, I think this would justify the investment. In principle, you could also utilize the heat from miners, but at such temperatures you might only achieve an efficiency of 10%. That is about 100 kilowatts from a megawatt. Well, it could be useful for something. We can also use any type of fuel as a heat source for our turbine. Since our fuel burns with an excess of air, the temperature is such that few harmful substances are produced and we don't have to worry about detonation and so on. For example, we can certainly use fuel oil and so on as a primary fuel source. And in the end, we can even effectively use firewood as a fuel, because if you carefully stoke the firewood well, you can indeed get a very good temperature. Yes, you certainly can. You absolutely can. Look, here's a very helpful link. Basically, you can indeed make a gas wall mounted or a floor standing boiler that runs efficiently on natural gas. At first, our specialized burner heats the working fluid for our Rankine turbine, and this gas can easily heat it up to a significant 500 degrees. Then, as a highly effective cooler, you can utilize the existing heating system, say at a comfortable 70 degrees. Opa! So with a delta of 430 degrees, we can achieve a pretty good efficiency. That means the gas boiler will generate electricity in addition to heat. So this can be used both as a backup system and as a main one. For example, if you have a gas supply, you can get electricity directly from that same gas. This isn't my invention. A similar gas boiler exists, but only based on a Stirling engine boiler was made either by Weizmann or BBD Ross. But theirs was more of a promotional product, because the price was truly outrageous, since to achieve a decent level of efficiency, they utilized a Stirling engine with hydrogen at extremely high pressure as the working fluid, making this compact because it's not cheap and doesn't really work out well. But in principle, it did work. There was something like 2 or 3 kilowatts. In general, many applications are possible. You could try using it with geothermal sources, geysers, and so on. To generate electricity, even if the temperature isn't 300 degrees, but more like 100 or 150. Since there's a lot of energy there, in principle, we don't really care about the efficiency. We're only concerned with the amount of power we get for a certain amount of money. Well, folks, I hope you enjoyed it. Subscribe to the channel and give it a like. All the best. Goodbye. Oh, getting old is just no joy. We're not just pathetic mere bugs. We are super incredible Ninja Turtles. We proudly wear our shells like protective shirts, always ready for action. It's fine, it's fine. If you stoke the firewood well, you can get a pretty decent temperature from it. I should have said that right. Exactly. Here you are. There's a lot of water here for protection. Mr. Bender Rodriguez, what are you doing here? Are you going to listen? Well, listen, let him sit down. So anyway.